Thank you very much to the organizers for this impromptu invitation. So a little disclaimer is that I had just a couple of days to prepare these slides, so I apologize in advance if they're a bit rough, and I ask you to please interrupt me if something is not very clear or if you have any questions. So today I will revisit an old, nice problem, that of nonlinear PCA. Usually by nonlinear PCA, what's understood is that this is the generalization of the standard PCA from straight lines to curves. And the goal is to recover the curve spaces that are inherent to the structure of the data manifold. Okay, and as I said, this is an old problem. To give a kind of historic perspective, I chose 4 references to put in this slide. So first, in the 80s, there was this algorithm called principal curves proposed by Trevor Hussey and colleagues, where they tried to fit a one-dimensional curve with some regularity to the data manifold. And then already in 1991, there were people proposing to use autoencoders to do the nonlinear PCA. Back in that day, they were called auto-associative neural networks. Then, starting in the late 90s, there was the wave of kernel PCA, kernel ICA, etc. And I also include this paper by Schultz, 2002, where they also use autoencoders to do the nonlinear PCA, but they care about having a hierarchical representation, which I will define more formally in just a minute, but the idea is like in standard PCA, we want to have an ordering of the components according to how much they explain the data space. And this is something that we have in standard PCA and in kernel PCA, but when we go to using autoencoders, this doesn't come for free, and this will be the main subject of this talk, is how to achieve this. Okay, so doing nonlinear PCA with autoencoders is very simple. We have an autoencoder, and we feed data in the input here from below, and we want to reconstruct the input. We minimize a loss, like the L2 norm, for example. But in the middle of the autoencoder, we have the bottleneck layer, where we only allow some information to go through. In the case of this figure, for example, it's just one latent variable. Okay, and if everything goes well and this autoencoder imposes some regularity, this latent variable should parameterize the principal curve that traverses this dataset. That's the one seen on the right. Now, if I add a second component to the latent code with this autoencoder and this dataset, this should be enough to represent the whole dataset. Okay. Now, so I said we want hierarchical representations. This means like in standard PCA, we have this ordering where the first n latent variables or components, they induce the n-dimensional space that best approximates the data points. Okay. Now, we will see next with more, so when we go to higher dimensions with more realistic data sets, how we can do that with the autoencoder, and we will have both the flexibility of the autoencoder and the ordering of the components that comes in PCA. Okay, let's start with a simple example. I have the MNIST database. I run it through a 2-dimensional autoencoder, and suppose I have in the middle layer, I can put a batch normalization layer, so my latent variables are normalized, and then I can sample from the latent distribution, and I can see what the decoder generates. And we see that in the case of MNIST, this is very nice because it's directly related to the class of the digits. So this is like what the first 2 principal components capture. Okay. So here I'm using two latent variables just for visualization properties. Okay. But now, okay, my two latent variables control the class, but because the bottleneck is so small, the reconstruction is poor and quite blurry. Okay. Now, if I want to go to a better reconstruction, I think of adding more latent variables. Now suppose I do that and I go until a representation of 16 latent variables. What happens is that, okay, I get a sharper reconstruction, but now the two latent variables that I had associated to the first two principal components, they no longer represent or control the class of the digits. So we lose this condition of hierarchy or ordering in the components. So in the rest of the talk, I will propose a very simple method to be able to grow the latent code of the autoencoder and still maintain this conditioning that we want. Okay, so this I call the Jacobian constraint. So we have two autoencoders. One was the first we trained, where we captured this nice two components related to the class in MNIST, for example. On the right, we have the autoencoder where we have enlarged the latent code. And what we would like to do is to transfer from one to the other the response of the decoder when I vary the latent variables, or the first latent variables as are specified by the first autoencoder. Okay? And this formally amounts to the partial derivatives of the output with respect to those latent variables. And that's why the name Jacobian. Now, usually we are dealing with images, so these Jacobians are too big to be computed with backpropagation. With backpropagation, I could get the gradient for 1 pixel at a time, and of course, this is totally impractical. So next, I will show you a simple trick on how to impose this approximation. So let's consider, as before, we have the decoder on the left. I will call it the teacher, and the one on the right who wants to learn its Jacobian is the student. Okay, so we have the teacher decoder F, and I do a simple Taylor expansion in the vicinity of a latent variable Z, and moving in the direction of the vector H. And now the decoder G, which was on the right, it has a larger input space, okay, of dimension k plus d, where d is the variables that I added. And so I will split that input dimension into a z part and a w part. And now the Jacobian for g, I will multiply it by a vector that has h in the dimensions corresponding to the same that f has, and 0 in the others. I don't care about how it varies on those dimensions. I only want to constrain it to vary the same as f for the first k dimensions. So now a simple rearrangement. I put the Jacobians to the left, and now by J bar here, I call J bar the Jacobian of G, but where I dropped the last columns, the last D columns, which anyway, in this case, they are going to be multiplied by 0, because I don't care about those directions, so I can just ignore them. And then I take the norm, so I can bound this quantity, which is the quantity on the left, is like the difference between the partial derivatives of f and j in the direction of h. Okay, and I can bound by these two terms, and now I can work with this because G here in blue is a neural network that I'm training, so I can make it make this term make it smaller just by adding this norm to the objective function of my training. Okay, so in this way we can constrain the partial derivatives, as I said, of f and j to be the same in the direction of h for the latent variables z. And in practice, what I will do for h is I will sample this from the data itself. And I constructed it by selecting a couple of random samples, and this makes this approximation. So by sampling from the dataset, this makes it care about the directions that are relevant to my dataset. Let's see a bit more in detail how what is the loss function that I will train for my network. So remember, we are training for G. F is fixed. It's like the first autoencoder that we train, which has captured the first principal component. And G is the new one, where we want to transfer the Jacobian of the first part. So the loss function is composed of 3 terms. The first one is just the reconstruction loss. So now I'm calling G hat the full autoencoder, and G prime and G the encoder and decoder respectively, and the same for F. So the first term on the left is just the reconstruction. The second term is the one that comes from this bound, it's just the difference of the differences. And the third term comes from the fact that so far we assume that F and G saw the same Z. This is not the case necessarily, so I need to enforce this. That's what the third term is there for. So this is what I propose in this paper that will be presented in iClear next month. So more details about the formulation and technical details about the implementation can be found in the paper. Okay, so let's see what happens now. So in what follows, I will call the leftmost term the reconstruction loss, and the combination of the second and third terms the Jacobian loss. Right, so let's see what happens. So here I show the performance during training in the test sets. So on the left, we start with the 2-dimensional autoencoders that has already captured the first 2 principal directions. And each vertical bar indicates the moments where I grew my latent code by 1 variable. And as I grow the latent code, of course, I get better reconstruction because there is more bandwidth for the decoder to make the reconstruction. And the orange curve shows the Jacobian loss, which maintains this conditioning of the Jacobian and propagates it through all the successive steps or stages of the progressive growing of the autoencoder. And so as a result, we get the autoencoder with a 16-dimensional latent code that we wanted, and we get the sharp reconstruction, but we haven't lost the control of the 2 principal variations related to the class. And we can also visualize what are the factors that are learned in the middle as I grow 1 by 1 my latent code. So here I show for 3 different samples. I fix all the latent variables except the one that I want to play with, and we see that, for example, the third factor is related to the width of the stroke, and the other ones are related somehow to the style of the handwriting. Okay, so that's the idea. So maybe some of you are thinking that this is something that this is a very easy dataset. Maybe PCA will do the same. So let me show you a dataset that is a bit more complicated, which is the Street View house number dataset. Is similar to MNIST, that we have numbers from 0 to 9, but we have many other factors of variation, like the lighting, the color, the contrast, typography, and we have also other numbers appearing on the sides. So when I train a 2-dimensional autoencoder to recover the first 2 principal components, what I get is this. So now instead of capturing the classes, it is just capturing the lighting and the shading of the images of the digits. So for example, if we go from left to right, we go from darker to lighter, and if we go from top to bottom, we go from light from the left to light from the right. Okay. So now let's just keep adding more variables and see what we discover. And it turns out that when I arrive to the 8th and 9th components, I find the latent variables that are related to the class. So now I can put one image and fix everything else except the 8th and the 9th factors and change the digits in the image while leaving the style constant. And I show here 4 examples of that. Another way to visualize that is to plot the actual values of the latent variables when I encode the data. So this is for the test data, for example. And for the first and second components that we saw were related to lighting, this has nothing to do with the class. So when I plot using the class colors, everything is mixed. Now when I go to the 8 and 9 factors, this is where we see the classes appear. And well, to me this is a very nice result because this was done completely unsupervised. So I only used the labels to make the plot. Okay, but the algorithm just digged away the distracting factors until it struck the information that we wanted to see, which is the class information. And in comparison, if I do just a standard nonlinear PCA, and I try to find the factors that are most related to the class, this is the best I could do. So to me, even though the clusters have a room for improvement, this is, to me, a very promising result. And as a sanity check, I go back, once I have trained the big autoencoder, I go back to playing with the first 2 components and make sure that they still encode the two factors of variation that were found by the first autoencoder that are related to light, going from dark to light and light from the left to light from the right. Okay, now I will move to a bit of a different application, but using the same idea. And I will cheat a little and use some supervision to specify what each latent variable relates to. But so the dataset here is the celeb A dataset. It's like 200,000 images of celebrities taken from the web. And each image has 40 attributes annotated, 40 binary attributes, like eyeglasses, no eyeglasses, male, female, young, old, etc. So what I do now is that I will ask the autoencoder to predict these attributes in the latent code. Okay. And for the first autoencoder, I will give it a short latent code. So the decoder is forced to read that information from the predicted attributes in the latent code. And that way, the autoencoder on the left, with that autoencoder, I will be able to, by playing with the value of the latent variables, to manipulate the attributes in the resulting image. But because the latent code is short, the output will be blurry. On the right, we have an autoencoder with a longer latent dimension. The problem here is if I don't do nothing, I don't know how the decoder is going to read that information. I might just shortcut the predicted attributes and make the reconstruction from wherever he wishes. So I want to impose the conditioning that the first autoencoder has, and I do this with the Jacobian constraint. So let's see some qualitative results first, and then some quantitative. More examples are in the paper. So this is the reconstruction. So this is the result for the rightmost model. So this model, the model on the left is good at manipulation but bad at reconstruction. The model on the right is good both at manipulation and reconstruction. And I'm showing the results for that one. So the reconstruction is already quite nice. Whoever has worked with autoencoders knows that they tend to have blurry reconstruction, so I think this is quite nice. And then we can play around with the attributes by changing the values of the latent variables. So we can go from male to female, add glasses, remove glasses, etc. And also the nice thing about it is that we can have a continuous control of these attributes. So I can build an interface like this. This is a screenshot from a video that it's available on the web page of the paper, and there is also the code for for doing this, but here we have sliders where we can control smoothly each one of the attributes and condition the result on that. And for some quantitative results, so in this graph, I'm showing on the horizontal axis, I'm plotting the reconstruction error, so better to be to the left. And on the vertical axis, I'm showing what I call the disentangling score. This can be measured by using external classifiers that for this particular dataset, they exist, that can predict the presence or absence of the attributes. So with that, we can quantify how well our model, how good it can manipulate, like turn on or off those attributes. So we start with the, in this graph, the top left is where you want to be. That means that you are good at reconstruction and good at manipulation. So we start with the model on the black square. This is the teacher that has the short latent code. It is bad at reconstruction, but it's good at the disentangling. And then we duplicate twice the length of the latent dimension. And because we're using the Jacobian constraint, we maintain the ability to manipulate the attributes. The blue curve is an alternative method based on the cycle consistency loss. I leave the details for the paper, but it's another way to go for the disentangling. And now when we add more dimensions to the latent code for that model, the decoder starts ignoring the attributes that we wanted to specify. And the star is fader networks, is a method proposed by Facebook, which was the state of the art for attribute manipulation in this dataset when I wrote the paper. And what they do is they use an adversarial discriminator in the latent code to make it like forget the information about the attribute and force it to read that information from some latent variables where they inject it manually. And it's a method that works very, very nice when you have just a single attribute, but when you start adding attributes, it starts giving poor performance, mainly because the adversarial discriminator acting on the latent code, it starts harming the reconstruction. So I went fast. Okay, in summary, so we introduced a variant of nonlinear PCA. So we saw, for the nonlinear PCA, we wanted to have the ordering of the components and as well as the flexibility of the autoencoder. And so we show how can we achieve both by growing the latent code progressively and imposing the Jacobian constraint. And we show also that this Jacobian constraint is helpful to address, to overcome the natural trade-off between disentangling and reconstruction that exists in autoencoders. And I can think of many possible applications for this. Of course, well, data visualization is one. Of course, when you have disentangled representations, it will be helpful for other downstream tasks. Clustering, now we can imagine that as in the SVHN case, if we identify factors that are just distracting, we can remove them. The same goes for multimodality. If we can identify the factors that are intrinsic to each modality, we can remove it because we don't want to work with them. And then for the example I show of conditional image generation. And now, before going to your questions, I will also like to do some advertisement. I'm very happy to announce that we are organizing a Latin American meeting of artificial intelligence with a summer school in November of this year in Montevideo. So nice weather and nice place. And we have an amazing list of confirmed speakers, including one Turing Award. And so, so the idea is to gather the Latin America community, but we would like to see people from all over. So we welcome every interested student to apply or to pass the message along. The web is kipu.kh.ai. And now I can answer your questions if there are any.
Thank you, José. Is there questions?
Thank you first for a nice presentation. I had a question with respect to the Jacobian constraint that you're giving. Do you think it would be possible to do to construct an autoencoder where by design you would have this the stability of the variation with respect to the first component? Because, for example, you were kind of saying that the issue with the teacher model is that it's kind of blurry. So you could hope to just add up the details without modifying the much.
Yeah, yeah. I don't really know how to do it without this like progressive. If you mean if you can
that's
do it,
what I'm thinking about.
If you can do it at once, that would be a really cool solution. I don't know. Right now, I don't know how to do it. Okay. Thank you.
Another question.
Bruno here.
When do you decide to add a dimension, and do you think about several criteria, for instance, delaying the time when you would add a dimension, or all these things? Is there some problems to be solved there?
So I'm not sure I understood the question entirely. So you mean when to decide to add or not to add?
Yes, during the growth, when do you start adding a dimension?
Yeah, so maybe one easy thing to do is to monitor the reconstruction error, and when it stagnates, is that there's no more information to get from the data. And yeah. I'm not sure if that was your question, or if not, we can discuss it later.
Thank you.
Thank you. I think there was another question behind it. No. No. Oh, thank you. Marcel.
Hi, thank you. I really enjoyed the presentation. I was wondering if, as a sanity check, you had the time to do like linear PCA or something like that. And
yeah, of course. Yeah, but for both, for these simple data sets, just by using the autoencoder, you get this nice distribution of the latent variables that you don't get with it. You get something similar, but not as nice for MNIST, and for SVHN it's even worse. So the nonlinearity is really helpful here.
But the variance, is the ordered components that you're getting do have like higher variance on the manifold. Like when you do PCA, the first component has highest variance and then so forth.
Yeah.
And you get the feel that this is indeed happening with by progressively growing the network. I know that's the motivation, but have you had the opportunity to do any tests to see if indeed this is happening?
So I don't know, maybe like measuring the average reconstruction error is like measuring the variance in some way. Okay. So this goes down, so it's not sure I also, if this...
No, I think you're right, yeah.
That's it. Okay. Well, thank you, José, again.